So here we're going to talk a little bit more about the what and the why in terms of this and any other cell in terms of why the electrons flow and what that means. So scrolling back down here, the rate at which those electrons are flowing or going through the wire is defined as electric current. That's going to be measured in amps, and that is in an amp is 1 coulomb, which is our unit of charge per second. So a coulomb, and we will see this, is the charge of actually a whole bunch of electrons. So it's almost 100,000 electrons per second that's flowing when we have an amp. But in terms of voltaic cells and electrochemistry, the more important thing is actually the potential difference, or what we call the voltage. We could think of that as like the push or the potential energy per electron that's pushing the electrons one way or pulling them. It's a measure of the thermodynamic favorability. So as we look at all of these, if you're doing physics, there's a whole bunch to understand the what, the why, the how on this. But really, we just need to focus on voltage as an idea of joules or energy per charge as a relationship of how favorable a process is. And when we do that, we define it in terms of cell potential or voltage of our cells. So the difference in the voltage between our two electrodes gives us our overall voltage for our battery or for our voltaic or our electrolytic cell. It all depends on how easily the different things either gain or lose electrons. And as we do that, we have to have a point for comparison. When we're doing that, we're thinking about standard conditions. 298 in terms of Kelvin, 1 atm in terms of pressure in case there's any gases involved. But mostly what's important is we're talking about 1 molar solutions. So that copper solution and the zinc solution up above with those pieces of metal would be 1 molar solutions. If we have a big positive value for a cell potential, that means that it ends up being very favorable. We are producing a lot of voltage. So cell potential for our purposes can kind of be synonymous with our voltage. If we have a negative value, that's how much we need or how much would be needed to cause this to occur. Those are not favorable, and they require that much voltage to be put in or that much electric potential to be added in order for the reaction to occur. But because these things are just a comparison of how likely something is going to be oxidized or reduced, we need a place to compare them to. And our comparison is kind of a middle of the road reaction in terms of gaining or losing electrons. It is taking a hydrogen ion and reducing it, gaining an electron to make hydrogen gas. We define that as a voltage of 0, not because it doesn't require or release energy necessarily, but just for comparison. We think, is everything else easier to reduce or harder to reduce than a standard hydrogen electrode? So 1 molar H plus, we're talking about a 1 molar solution of an acid, maybe hydrochloric acid, gaining the electrons to make hydrogen. Everything else is compared to this, and in a question, you'd either be given a table with a whole bunch of reduction potentials, or you would be given just the ones that you need. So these values are always going to be, by convention, given as reduction potentials. So we'll see this here. This is actually the one that they used to give on the AP exam. It was right up there in the front with all the different reactions and periodic table, all the different reduction values from reducing fluorine to fluoride ions, which has a very positive voltage. So that half reaction produces a lot of electric potential, all the way to taking a lithium ion and turning it back to lithium metal, which is very hard to do. Lithium does not want to be reduced. And notice these are all reduction, so we can compare them all in terms of their ability to gain electrons. They either gain better than hydrogen ions do, or they gain worse. For these that are worse, we would think of them as not wanting to reduce, or more simply, things that do want to be oxidized. So if we come back here and we look at zinc and copper, right there is our hydrogen. The copper is a little bit above. 2 copper ions gaining 2 electrons to make copper metal has a positive standard reduction potential of 0.34. It wants to be reduced, and in doing so produces a certain amount of voltage. But zinc is down here. It doesn't want to be reduced. So copper has a positive value, meaning it's more likely than hydrogen to be reduced, as I said. Zinc's negative means it's less likely. But since it's less likely to be reduced, it's also more likely to be oxidized. So as we're thinking about this, we're looking at always a reduction potential and thinking of the thing that is most likely to be reduced, the most positive of the standard reduction potentials is the thing that gets reduced. The least positive is going to be oxidized. Or we could say least negative and most negative, but really the higher it is up on the list, the lower it is on the list. If it's formatted this way, it can tell us what's reduced and oxidized. But remember, they're not always put in order, and they're not always put in a chart that's most positive to most negative. But what we do to find our overall voltage, we've seen that graphic a few times, and it always shows it as 1.10 volts. The way we can figure that out is think about, well, what's the standard cell potential for our cathode, the thing that does get reduced? In this one, it was copper ion to copper, which is 0.34. But then we do a minus here, cathode minus anode, because rather than reducing my zinc, I'm actually oxidizing it. So the minus the negative is kind of flipping that reaction for us. We keep it this way so that no matter what we have to solve for, we don't have to think in our heads about what needs to get flipped or why or how. We always are just going to do cathode minus anode, to give the overall cell potential. Right here in purplish, I have a special notation that you're not going to see on the AP exam, but you will see maybe on some online questions or in a textbook. That's standard cell notation. It just shows us on the left what is being oxidized, on the right what is being reduced, and those single and double lines are kind of dividing our different cells. Once again, we won't need that, but we can think, okay, the zinc is going up in charge, that's oxidized, so that's my anode. So the value for zinc is the second one. The copper is being reduced from +2 down to 0, and that's right up here just off the screen being reduced at the cathode. For voltaic cells, for galvanic cells, remember that means the same thing. It's always thermodynamically favorable, and your cell potential is always positive. So as we're trying to set up a thermodynamically favorable cell, we always want it to come out positive, or I'm saying always a lot here, we would take the higher, the more positive reduction minus the more negative reduction. With these, the voltage does not change as I balance this. Copper and zinc are such a common example that I use that, but we'll see some down here where we actually have to balance our reaction. We'll do those examples together. And when you do that, to combine it overall, you might double one reaction, but not the other, or triple, or times 5, or divided by that. Some important things there is even when we balance it to balance the charge and balance the electrons, the voltage doesn't change. And we can come back to the definition of voltage for that one more time. Voltage is electric potential energy, joules per charge. So if I put in more of an element, I actually get more energy, but it's also more electrons, so more charge. We don't need to remember or define that exactly, but it is important. This is an example where we're kind of combining reactions. We are combining reactions, but unlike Hess's law with thermodynamics, we don't double our values. They do end up getting reversed with this negative sign, but we don't have to double them or cut them in half because of the definition of voltage.